effect. But in this today, I never talk about for the hydrodynamics. Just say about for the special relativity and general relativity. What the meaning of this one today. I hope you can catch up for this essence of this one. So the first is a brief review of the special relativity. So the special relativity, writing for the SR, is a physical theory of the measurement into the inertia frame of the reference. It proposed into the 95 by the Albert Einstein. It generalized is Galileo's the principle of relativity, that all the uniform motion is relative, and that there is no absolute and well-defined state of the rest, so no predicted reference frame from the mechanics to all the law of the physics. So in addition, the special relativity incorporates the principle of the speed of light is the same for the all inertia observer, regardless of the state of the motion of the source. So this is a brief review of the special relativity. I try to jump in a little bit more detail. So simple postulate here. The law of the physics are the same in the every inertia frame of the reference. So this is, we say, the principle of the relativity. And second point is here. So this is the speed of light is in vacuum is the same in the all inertia frame of the reference, and it's independent of the motion of the source. So this is the invariance of the speed of light. Special relativity have this two postulate. This is the most simple idea about what the relativity things. Consequence of the special relativity, I try to write down for a little bit about there. So maybe you may know about for the time dilation. The time lapse between the two events is not invariant from the one observer to the another observer. But so it depends on to the relative speed of the observers. This is the reference frame. Second point is the relativity of the simultaneously. Two events happen in the two different locations that occur simultaneously to the one observer. But it may occur at a different time at another observer. So it means the lack of the absolute simultaneously. So one event that happened for the, if you see about for this observer, yes, this is happened for the simultaneously over there. But if you see about for the another observer, oh, this is happened for the different times there. So this is time is also different. Lorentz contraction. The dimension, so like this, the length of the object as measured by the one observer may be smaller than to the result of the measurement of the same object made by the another observer. This is making for the Lorentz construction. So the special relativity, everything relative. We have a coupling with the time and the space. So this is making for the time is not absolute. We can delay it. And space is also construct based on the dependent on the observer case. And also the composition of the velocity. So this is the velocity and the speed is do not simply add. So for example, if the rocket is moving at the 2/3 of the speed of light relative to the observer, and the rocket fires the missile at the 2/3 of the speed of the light relative to this rocket, but this missile does not exceed the speed of light. So this is relative to the observer. So most fastest speed is light. Then everything does not exceed up to this speed of the light. So every time this is not a simple added, this is also some contraction. Inertia and momenta, as the observer's speed approaches the speed of light from the observer's point of view, it must appear to the increase, thereby making it more and more difficult to accelerate it from within the observer frame of light. So of course, this is similar to there. If you can make it for it accelerate it faster, you can reach in for the near the speed of light, and then this is more difficult to accelerate it to further to there. And then this is same as the equivalence of the mass and energy, so E equal mc square. So this is a conservation of the energy. It implies that any reaction decreases the sum of the mass of the particle must be accompanied by increased kinetic energy and the particle after the reaction. So this is the consequence of the special relativity. So maybe if you read about some book of the special relativity, maybe you can see the more detail about for this kind of concept. Okay, so this is the one case I can just show about the Lorentz transformation. So this is if think about for this x, y, z. This is one of the static point. And then if you moving about for to the x prime, y prime, z prime, this is moving with the constant velocity v is along to this is one of the frame. So this is the frame difference is changing from to this one to using for to the velocity. Then this is best velocity is getting for the discount to the formula to the transform. We say this is Lorentz transformation. If you write in for to the metric way, this is Lorentz transform metric. Then Lorentz factor gamma is famous to the 1 minus b square over c square, 1 minus b square over to the c square, the value to there. So here I can write in for the gamma, it's a gamma, but sometimes maybe tomorrow I'm say about for the Lorentz factor writing for the w, because this is the numerical relativity guy. It's mostly using for to the w to the Lorentz factor instead of the gamma, it's normal one. So this is the Minkowski line element. So flat space-time, we say this is now we are living into the flat space-time. We say this is a Minkowski space-time. So space-time is here. So event, it's everything happen for the time and also 3 space. But in the relativity and the special relativity, we are thinking about for the space-time. So that everything is coupling with the time and the space. Then after that, we can get in for the all set of the event. It's based on to the space-time happened. Here is a special relativity. We are thinking about for the flat space-time. Flat space-time, we can say about for the Minkowski space-time. Then the metric is written to like this. So ds square is a metric is making for to the interval with the between to the 2 event point. So this is getting for the d square square. It's minus c square dt square plus dl square. dl square is getting for the this is a similar spherical coordinate. This is dr square plus r square d theta square plus r square sine square theta d phi square. So I think this is a famous of this one. So maybe after that I can also talk about for the spreadsheet black hole, then easy to recover to something. Okay, so this is also coming for the here. So now it's all event. It's if something happens for the event, then this kind of information is everything is propagated at the light speed. So we know to the light speed it's most fastest speed into the here. Then this is now making for the one of the cone to here. We say this is the right cone. So this right cone is making for the what's the place over there. This is now its observer. So this is if this is inside here, we say this is a space-like region, and then inside here we say this is time-like region, and then along to this line we say this is right-like or near geodesic to there. Okay, so the experiment test of the special relativity. So special relativity is makes many predictions and which are well tested. Now it's listed up for some tests over there, and then the most well tested is a particular tested one is the isotropy of the light speed. So it's starting for to the Kelson-Mori test, and then starting for some laser MEDA test or something. So now it's still we say special relativistic it's well valid, well tested is a theory. So law of the physics in special relativity. So that physics, law of the physics in the special relativity, it's written them as a tensor equation, because the tensor the Lorentz covariant entirely. So we try to follow everything if see about for the different frame, everything easy to changing for the Lorentz transform. But the classical Maxwell theory, it's written to the electric field and the magnetic field, E and B field. But this is not a covariant of the Lorentz transformation. So using for that to consider about for this special relativity, we need using for the tensor. Then this is using for the Faraday tensor to including for the magnetic field and the electric field. This is 4-dimensional field. Then you can apply for the special relativity. Also, the using for the conservation of the energy and momentum, this is the simplest, and then derive the field equation, if possible, from the Lagrangian. But this is also going to the general relativistic thing. So important point, even for the special relativity, we can consider for the tensor equation. this is easier to write in for the law of the physics into special relativity. Okay, so this is the summary of the special relativity. Because the special relativity, I think the most of person has already learned something. So maybe I try to quickly. So special relativity 1905 is well established. Invariance of the speed of light is well tested, and no preferred frame reference in the Minkowski spacetime. This is a flat spacetime. And the law of the physics are to be written in the covariant way, and the Maxwell theory of using for the Faraday tensor or something like this. And then the question is coming. So how to include gravity? So this is the motivation to moving for the special relativity to the general relativity. Okay, do you have any question until to the special relativity? If it doesn't have, I can join to the general relativity. Okay, so moving for the general relativity.
Covariant and contravariant form, is that clear for everybody? If it's not, Yosuke can explore this issue.
Yeah, this is
can comment on this. Okay.
I mean, we need a whole course of relativity. Right?
Yes, that's if think about this one. So I try to.
It's hard to in 5 slides to understand if you haven't seen it before.
Yeah.
But it's a great exposition. Yeah. So
yeah. Okay.
I think it's important that ask questions or discuss after the lectures.
Yeah. Okay.
So
yes.
Students, this is for you. Discuss. If you haven't seen relativity before, you will not be able to follow this very well. But try to pay attention to the key points that Yosuke is pointing out.
So I think this is give to some concept. I couldn't write in for the many detail or some tensor calculation or something like this. Maybe you can catch up for what's the meaning of the special relativity, what's the essence of special relativity, or general relativity. After that, I can talk here. Okay. So it's from the special relativity to general relativity. So essence of the element of special relativity is only to the local concept. So this is concept of Minkowski space-time, and also concept of the metric. We say this is talk about here. For the distance measurement, this is notation of the geodesics, and a little bit talk about later. And also the causal structure of special relativity is induced by the metric. This is also local Minkowskian. So how to incorporate up to this gravity? So simply the general relativity using for via the equivalent principles, then going to the geodesics, and then going to space-time as a manifold of the event. I can talk about for this each point. It's step by step later. And then so general relativity is using for the rich tensor to couple to the all type of matter, but many other metrics also theories can be applicable. But this is just the simple overview of the GR, but I try to give to some more detail after that here. Okay, first talk about for the equivalence is the principles. So equivalent principle in the few common words is all things fall in the same way. So this is a concept here. So, or slightly more wordly, so all objects have the same acceleration in the gravitational field. So the feather under the bowling ball is followed with the same acceleration in the absence of the air friction. But I think many one has known about what the meaning of this one. I think. Also, the fact that all things fall in the same way is true because the inertia, the mass that enter the Newton's law of the motion is just only F equal to ma, is the same as the gravitational mass that entire the gravitational force of the law is current. And also that this principle of the equivalence is the reality to the statement that the inertia and the gravitational mass are equal to each other for any object. Okay, so the Einstein's exchange principle is shown above for the three concept. This is the uniqueness of the free fall, and also the local Lorentz invariant, and local position invariant. And then based on this is the to follow to this equivalent principle, I doesn't say details so much about here, but the metric theory is one of the definition in the GR. Why we are using for the metric theory? Because this is just only the theory to be able to above for this Einstein's equations principles to follow to that. Because to that GR, it's going to the from to the flat spacetime to the curved spacetime. Then curved spacetime, it's making for to the some Riemann manifold. This is more mathematically we can return to using for to the tensor theory. Then this is a metric. It's only one of the useful mathematical tool to apply for this GR. So curved spacetime, sometimes we say the Riemann manifold is endowed with the symmetric four-dimensional matrix. And then this kind of trajectory of the free-falling body are the geodesic of the matrix. This is one of the mathematical point of view. So I can talk about a little bit later to the what's the geodesic to mean about for this general relativity. Okay. So general relativity and the equivalent principle. So Einstein started to think to the path of the object as a property of the space-time itself, rather than to the being to the relative with the specific property of the object. The idea is that the gravity is manifestation of the fact that the object in free falling follow the geodesic in the curved space-time. So what's the geodesics? Okay, so that we know is our ordinary experience. So like this, we are living to the flat Minkowski space-time. That into the absence of any force, object follow to the straight line to this one. And we also know that the straight line are the shortest possible path that connect the 2 points in such a condition. Okay. Okay. Yep. Okay. So this is a generalization of the notation of the straight line. This is valid also in the curved spacetime to the Riemann manifold. It's called a geodesics. So that this is a flat spacetime. Every time we can most shortest path is making for the straight line over there. But in the GR, this is looks not a straight line, but this is the most shortest line because this is along to the geodesic motion. So because this is something is weird, but this is one of the concepts of the from to the flat spacetime to changing for to the curved spacetime. So I try to explain a little bit about for the ant on the apple. So this is one of the famous story to simply illustrate the idea of the general relativity. Is a parable of the apple by the Meissner-Thorne Weird. This is a gravitation. It's a famous book. Sometimes say about for the telephone book or something. Then this parable is try to explain the nature of the gravitation in the term of the curved spacetime. And then the spacetime of the parable is the two-dimensional curved surface of the apple. So there. Okay, so this is the important point of this picture is we can follow about there. Okay. So first, the tale goes like this. One day, a student reflecting on the difference between the Einstein's and Newtonian's views about the gravity noticed ant running onto the surface of the apple. By advancing alternately and of the same amount of the left and right legs, and ants seem to take the most economical path to along to this apple. Well, they are going to along the geodesic on this surface. Okay, this is the idea. The student followed the path on the ant, tracing it and the cutting with the knife on the small stripes on the trace. Indeed, when put on the plane of the path, this is a straight line. So this is here. So this is ant. It passes onto the along to this apple, but apple is of course this is a three-dimensional curved. But if you see the magnified this view, cutting from this line, yes, this is just only for the straight line over there. Then so the each geodesics so may be regarded as a path, so word line of the free particle on this surface. So this is taken the two-dimensional space-time here. So now we just think about for the three-dimensional some curved space-time. But if think about for the two-dimensionally magnified at some local view, this is making for the straight line over there. Okay. So the student is look at the two ants going from the same spot onto the initially a divergence to the path. But then when approaching to the top, we say this is the top. Then near the dimple of the upper, the path is crossed and the continue into the different direction. So this is around to the top. So this is one of the ants is passing to the over there, another ant is passing to like this here. But this is something like the crossing of this top of here, but they continue to a different direction. The reason of this is curved trajectory is according to the Newton. So gravity is acting at the distance from the center of the attraction. So like this, in the upper case, this is the top region is the center. Then this is distance from this top region. According to the Einstein, this is local geometry of the surface. This is around the dimple. It's curved. So this is two different pictures there, coming from the Newtonian view and Einstein's view. Comment is here. So Einstein interpreted dispense with any action at a distance. Although the surface of the upper is curved, so if you look at a local spot closely within the magnified in the glass, its geometry looks like that of the flat space-time. So we say this is a Minkowski space-time or special relativity. Then the interaction of the space-time and the matter is summarized into the Wheeler's favorite words. So space-time tells the matter how to move, and matter tells space-time how to curve. So this shows the influence between the matter and the space-time. This is the most biggest concept of the general relativity. It makes the Einstein field equation is nonlinear and so become hard to solve. So important point is that previously before the Newton law, matter and space-time is a different object. But in the general relativity, matter and space-time is mixture, and also the both each other interacted in the interference. Then they making for the different picture there. So here the important point is yes. Okay, so this is one of the local point. If you, of course, we are think about for the curved space-time around to the upper, but if you magnify it here, we can locally view it's just a flat space-time. This is also one of the important point of there. Okay. So this is a summary of this parable. The object is follows the geodesics, and locally geodesics appear as a straight line. And over more extended region of the space and time, geodesics originally receding from each other began to approach at a rate governed by the curved space-time, and this effect is geometry's matter on what was called the gravitation. So gravitation is coming from the curving of the space-time. So this is the concept of the Einstein's GR. Then how to change how to curve to the space-time? This is depend on the matter. So matter in terms that the geometry. Okay, so this is a concept of the geodesics, and this is curved space-time based on the making for the gravity based on this GR. So do you have any question?
So this parable was proposed originally in the Misner book.
I think so, yeah. I also, unfortunately, I couldn't check in for the original one to coming from here. I also catch up for some others. Yeah, maybe I haven't deeply reading about for the gravitation is a book to found this one. So maybe somewhere.
Very long book.
Yes, this is. Yeah. Usually, it's very useful to using for the reference of some concept of relativity if you have some question to see about for this.
Yeah, it's there.
Yeah.
I mean, it's big one and with a lot of blah,
Yes.
blah, blah. That's very useful to understand.
But it's also the caution is sometimes the notation we are using for the Greek word is different. It's sometimes misunderstood or sometimes confusing compared to another GR book. Yeah, of course, this is yes.
As always from the beginning he tries to
Yeah.
distinguish. Yes, most
Yeah.
books tries to the Greek and the.
Yeah, this is, yeah, of course, if you see about for the reference, you can see what the meaning of this one to each word or something, but this is something. Okay, so there. So Einstein's equation of the general relativity. So now I give to some concept of the general relativity. It's here. Then, so based on this understanding for this concept, we need some mathematical way to include it here. So I try to avoid as much as the equation in this talk because we try to catch up for some essence of this general relativity. But I try to introduce a few things. So important quantity in the general relativity, the first one is the metric. So the metric is tensor is related to G, which may be regarded as the machinery for the measurement of the distance. So typically, we can write in for the G mu nu, the dx mu dx nu. This is the four-dimensional way. A Greek word is four-dimensional. And the ijk is typically, this is a three-dimensional. Curvature. This is expressed by the Riemann curvature tensor. This is written to this kind of way. And then this is the capital gamma, alpha, beta mu. It's also coupling with the metric term with the metric derivative term. This is so-called Christoffel symbol. It's also meaning about for some curvature up to the space-time. It's sure about this one. The rich tensor, this is the contract of this is the one part. This is here, and then also the curvature scalar, or sometimes we say the rich scalar. It's also this is contracted here. And also the covariant derivative is a derivative that take into account the curvature of the space-time. So we are usually taking to this one. So is Einstein's equation and general relativity. From these quantities, the path of any particle can be calculated. This is how geometry tells matter how to move. So this is Wheeler's word. The other direction, so the matter tells space-time how to curve. It's required to know about the distribution of the matter. So matter is including for the mass, energy, and also momentum. And this is described through to the stress tensor, stress energy tensor T. I can also talk about the detail about this T also. After many years of thinking, so Einstein reached the satisfactory form of the equation relating with the geometry and to the matter. So this is Einstein tensor. It's equal to some constant time to the energy momentum tensor. The Einstein tensor, usually we call to the G, is a tensor in the four-dimensional space-time, and that have a wanted property of being a symmetry tensor, because it must because the stress tensor is a symmetric. So we should be to the Einstein tensor is also the symmetric. Having vanished is a covariant divergence. It must be called the stress tensor is also have a covariant divergence. This is same property should be given with this Einstein tensor. And this weak field limit Einstein equation give to the Newtonian Poisson equation from the comparison with the value above the constant it found, because this is a general relativity. Going back to Newtonian gravity. So because this is also including for the Newtonian gravity information. So this is the Einstein field equation. I just show here, but I never use this one. Because of course, if you know about the solution to get in for the Shibashi black or something, you need coming from this one. But here I couldn't show about that. And also about for the 3+1 formalism of our simulation, but my simulation just using for the metric static. I doesn't solving for the Einstein equation, so we doesn't solving for this one. But if you want to know, or if you want to coupling for the Einstein equation, also we have a bunch of the reference or the work to do that. So maybe you are interested, try to read for some text.
What is your suggestion for if somebody wants to study numerical relativity? What is your favorite reference?
Favorite reference, of course, is our Redor's book is also comprehensively written about for how to solving for the Einstein equation, and also the I think it's another. I forgot the one. The living review is also.
It has the hydrodynamic.
Yeah, this is regular path is only for the hydrodynamics, but this is also extension to MHD. First, you need this is one of the big field to how to solving for the Einstein equation with the numerically stably to calculate there. This is a very big topics over there. Still, we are using for the several different formulation to solving for the Einstein equation. Of course, it's originally starting for the BSSM the formulation, and now it's using for the GZZ4 or something. I forgot. This is a more advanced way or something. But this is doesn't touching for this lecture. Okay, so this is the Einstein field equation. So this is G mu nu. This is the Einstein tensor. It's written about for the meaning of the space-time, and then including for the rich tensor, and this is curvature scalar, a coupling with the metric term. Metric is also say about that. This is measure of the space-time distance, and this is equal to the matter and the field. This is coupling with the energy momentum tensor. So this is the most simplest form. Now we doesn't including for the any cosmological constant, and energy momentum tensor it's written to here. So this is the less mass density, internal energy, also the gas pressure, and including for the for velocity to there. Of course, this is only for the hydro I can write in. If you think about for the magnetic field, we can add to the magnetic energy inside to this energy momentum tensor. On trajectory of the free falling to the body, we say this is falling for the geodesic. So this is the geodesic equation to there. This is including for the affine parameter, and then the Kurzweil symbol to getting for some position information there. Okay, so the some verification, a prediction of the general relativity. So the general relativity show about for the gravitational redshift. This is changing in the frequency of the light moving in the region of the difference curvature. It is measured in the experiments and taken into account by the GPS is currently. So, of course, now many one using for the cell phone and then checking for the Google map where you located about it. So this is using for the GPS satellite, and the GPS satellite also consider for this gravitational redshift, even for the very small part, but still we need to consider. Periastron shift. It is first measured into the perihelion is advance of the Mercury. This is the general relativity prediction is coincident with the anomalous advance if it's computed in the Newtonian theory. So we have some additional advance it happens there because this is related to the general relativity. So this is predicted this one, and then we can confirm. And also the recently the binary pulsar is also we are one of the targets to think about the testing of the general relativity, because this is much stronger field than to the normal this Mercury or sometimes things. So this is also becomes a more large shift to get in there. So now we also try to test it. Also this is the bending of the light. So the first measure is the bending of the photon is traveling near to the sun. And this is one of the prediction to testing for the general relativity. And then after that, we believe the general relativity it's correct the theory about it. Of course, now we are see about for the many gravitational lensing effect to see about for the huge galaxy or something. So this is already we know to use that. So maybe the GR is also nice. Of course, the problem for here, or most of this test is done by only weak field limit. We never checking for the strong field limit. So this strong field limit is also getting for the two possible target. One is the gravitational wave detection, and then our event horizon telescope to getting for the black hole shadow. So this is my yesterday talk is related about for the testing of the general relativity based on the black hole shadow. So this is one test to doing for the strong field regime result to the DR. Okay, so this is a projection of the general relativity. It's one part is a black hole. So black hole is literally a region from which the light cannot escape. So black hole is a stationary solution of the Einstein's vacuum equation, in which that the gravitational field is so powerful that nothing, not even as an electromagnetic radiation, can escape into the pool after having fall paths into the event horizon. So the term is derived from this fact that the absorption of the visible light renders the whole interior is invisible and indistinguishable from the black space around it. So if everything is black, then if you locate a black hole, so of course the black hole doesn't get in for any light, invisible light. So everything becomes black. So black hole, its name looks correct. Despite its interior being invisible, the black hole may reveal its presence through the interaction with the matter that lie at the orbit outside the event horizon. So everything is passing through the inside the event horizon. We cannot see anything, but still we can some interaction before to the outside of event horizon. Then this kind of the interaction is getting for the emission. Then this is shown above for the black hole shadow. So this is our current work over there. Also, there are several candidate objects that are thought to be the black holes. So I think it's even for our center of the galaxy. The galactic center is one of the candidates of the supermassive black hole. This is mass and also size is well constrained based on the stellar motion, but still we never detected no direct observation of the black hole in electromagnetic wave is up to now. So this is Event Horizon Telescope try to get in for the first direct evidence of the black hole information. But of course, recently detected the gravitational wave by the black hole merger. So we say this is a black hole. It's already some sense of the detection, or we say the observation of the black hole is through to the gravitational wave. We have already done. So it's another prediction of the gravitational wave. This is recently we have already found there. In general relativity, the disturbance in the space-time is curvature. This is old or this is gravitational field propagate at the speed of light as a gravitational radiation, or we say gravitational wave. The caution is here. So also we know the gravity waves. This is but this term was already using for the fluid dynamics, so with a different meaning. So I recommend to avoid it. So someone is confusing about what the gravity wave and gravitational wave. So this is, of course, especially like this our case. We are doing for the hydrodynamics also. This is coming for the gravity wave. It's many times happens to see, but of course the GR we are touching for the gravitational wave. So it's yes. Yeah.
Do you remember what are gravity waves in fluid mechanics? Do you remember what are the gravity waves in fluid mechanics?
The waves in the sea.
Yes, these are
Gravity waves. Waves in the water under the effect of the buoyant forces are like gravity waves.
I think yes. I have a lecture. It's a few years ago, but I forgot what's the meaning.
So it's not reaction of the Earth gravity.
Hmm?
Yep, Earth gravity. So the waves on the sea, we call them in the deep sea as gravity waves. Fluid waves under the action of gravity. So when you experience the buoyancy effects, you can call these gravity waves. You call these gravity waves.
Even in helical instability, we can say
As well.
Mm-hmm.
Actually, what happens is that when you talk about gravitational waves,
Mhm.
you are talking about a self-gravitating fluid,
Mhm.
and then the gravitation of the fluid itself is important. But when you talk about the gravity waves,
Yeah.
the gravity is external to the fluid.
That's yes.
the Earth gravity, for instance, and
Yeah.
is happening in the sea level.
Mm-hmm. So this is gravitational wave at a strong point to the general relativity, and which solve as action at the distance problem of the Newtonian gravity. So analogous to the light, so which is produced by the motion of the electric charge So this gravitational wave are produced by the motion of the anything. This is the mass and energy part of it. Then when your wave is hung, you're also making for the gravitational wave like this, because everything have a mass and energy, everything there. But pointed here, so the amplitude of gravitational wave radiation is very, very small. So it's quite hard to detecting up to this one. Then, so that recently, finally, we can catch up to the gravitational waves based on to the LIGO collaboration. So maybe this is big news about that. Maybe you know about for this one. Also, the recently also catch up for the neutron-star merger case. This is also very rare situation, and also the getting for the counterpart of this merger event. This is also very big advance out there. Okay, so the talk about for the black hole solution to here. So it's starting for to the Birkhoff's theorem. Birkhoff's theorem states that in the GR, any spherical symmetric solution of the vacuum field equation must be stationary and asymptotically flat. So this is a theorem. This means that the exterior solution must be given by the Schwarzschild metric. Also, this means that all spherical gravitational fields, whether from the star or from the black hole, are indistinguishable at a larger distance. After the larger distance from to this one, everything written in the Schwarzschild metric. Also, Schwarzschild metric is going to the asymptotically flat. It means it's going to the Minkowski spacetime. A consequence of this is that purely radial change in the spherical star does not affect in the external gravitational wave as a gravitational field. It means no scalar mode in the gravitational wave. So this is also we are confirmed to this one based on the detection of the gravitational wave. So, oh, yeah.
Yeah.
Actually, no, I am worried about this point that you said that all gravitational fields of a star or a black hole are indistinguishable at large distance.
Yes, indistinguishable. Yes, indistinguishable.
What happens is that if a star
Yeah.
is radiating, the solution is still spherically symmetric. In this case, we have a metric that is called the Vaidya metric. And then the Vaidya metric does not satisfy the Birkhoff theorem.
Okay.
Because outside of the star, we have the energy radiated by the star. And this is different of the black hole. And actually, this statement is right if you say that okay, you are neglecting the energy that is radiated by the star.
Okay.
And if you neglect that, then it's okay.
Yeah.
This is more difficult if the mass for stars of a very high mass, and then the radiation is efficient when you are outside, at least for a given distance. And then, in the absence of this radiation, okay, and then the solution should be Schwarzschild.
Yeah, I think it means that what's the exterior? It's mainly about what the distance from the center of mass, right? So we know the metric in the star, like the neutron star, and the black hole, the different near to the region. But exterior, it's of course I think I don't know the more than 100 Schwarzschild radius or 1,000 Schwarzschild radius. The difference between these two metrics is quite small, and then this is going to the Schwarzschild metric. So.
I think it's important to I think it's important to point out that Ademir is rigorously correct, but in practice it doesn't matter, right?
Yeah.
Because the radiation of the star will be a correction of 10 to the minus, divide the mass of the photon by the mass of the star, so I don't know, 10 to the minus 40.
I think
so you are correct, Ademir, by a factor of 10 to the minus 40.
I think, Rodrigo, that this is right for the majority of the stars. the majority of the star. But what he's telling is that if I have a spherical symmetric mass that don't radiate, this is equivalent to the gravitational field outside is equivalent to the black hole.
So this is probably,
and this is okay.
This is implicit in the large distance point, because at large distance enough.
But there are corrections. And so idea metric is exactly to take into account such corrections. Usually these corrections are small, but if the mass of the star is great enough, and then
I have a question about the Schwarzschild metric, because actually you are defining the Schwarzschild metric in this way. Isn't that so?
No, I think this is not defining. The Schwarzschild metric is one of the solutions. This is extended to this theorem. First is found to this one. Then after that, this theorems come up. As far as I remember. So I think it's so the Schwarzschild solution is that
this defines the Schwarzschild
Mhm.
solution.
Okay.
This is what I mean.
Okay. Yes, so the Schwarzschild metric is a very, this is a Schwarzschild metric. So Schwarzschild black hole is sooner after that the Einstein showed up for the general relativity papers. This is found with the solution. This is quite amazing. I don't know, I had some history about this one, because the Schwarzschild is originally from the Frankfurt. Is there. So the Schwarzschild black hole is a stationary symmetric solution of the Einstein vacuum field equation. And then so this black hole has a physical property only for the mass. So I later a little bit talk about also this one. So this is a Schwarzschild metric. I can write it into the Boyer-Linkes coordinate. This is the most famous coordinate try to use it. Then so this is I also use it for the minus plus plus plus. Sometimes using for the plus minus minus minus. But mostly I can use it for the minus plus plus plus. This is. But if you go into some Russian guy mostly like using for the plus minus minus. I don't know why, but it's yes. I don't like to just doesn't follow to the US style or something like this. But anyway, so this is we say this is a GTT term, GRR, G phi, G theta theta, G phi phi term. This is a metric component, and then this is only for the diagonal metric we have. Then this is GTT is 1 minus 2gm over r, and then GRR is 1 minus 2gm 1 minus 1, and r square r sine squared. So this is we say Schwarzschild radius. Schwarzschild radius is 2gm over c square. Oh, I think I drop off to the c square in this metric term, because usually I say c equal to 1 in the numerical simulation. So I literally drop off. But here is the definition of the Schwarzschild radius. I can also put onto the c square now here. And then it means the horizon radius. Also talk about it later. If r equals to infinity or mass equal to 0, so this Schwarzschild metric go to the normal flat Minkowski spacetime. We say this is asymptotically flat. And the property also keep into here.
So
Yes. Yeah.
So the student has a question.
Okay. Yeah.
He's shy.
When the radius goes to infinity,
Yeah.
the metric goes to Minkowski, right?
Yes.
But if the radius goes to infinity,
Uh-huh.
the metric should go to Friedman or something like this, not? Is just some
Friedman-Robertson.
Friedman-Robertson is including for the cosmological constant part. So this is the how to say is a cosmological way. We can put onto some cosmological constant based onto the Einstein equation. So here I say it's not including for the cosmological constant. So it's going to the Minkowski to there.
But this consideration can
Yeah.
change the behavior of our solution.
Yes, of course. Yeah.
Include the cosmological constant over there, it's going to change.
But not at small distances. The
Yeah.
cosmological constant
That
is
is-
only relevant at cosmological
But
scale.
we are
Yes.
talking about infinite distance,
Yes.
distance large enough. He's asking about very large distances. So
So asymptotic flat, it means that this is very large. I think it's a cosmological scale it means there.
And so maybe our theorems can be a bit
Yeah.
wrong.
Mm-hmm.
Approximate.
Yeah.
Or how much longer you can assume this
Yeah,
approximation. For
that's it.
instance, if you are studying a black hole far
Forgetting about
away from here.
cosmological distances. If you forget about cosmological distance, you are discussing, let's say, a local
Local case, yes.
universe with a black hole over there, then you are studying these large distances in this context.
Surely it is not important within our galaxy, for instance.
Mm-hmm. Yes.
You need to be
Local
in the
universe.
scale of clusters. And then after 1 megaparsecs, perhaps we may have small corrections
Mm-hmm.
due to the cosmological constant.
Okay. Interesting point. Yeah, I never considered about this kind of things, yes. Yeah, because I never touched the cosmological. Yeah. So I think based on that, this one also the how much is far from here is also that is the flat. This is depends on case, but if it's 100 Shivashi radius, already this is 100 times factor 2 difference. So it's factor 3 is a 1000. Maybe it's don't worry about the GR effect so much. So I think it's if you think about for the near more than less than 100 Shivashi radius, we should consider about for the GR effect. Or even for the if doesn't affect so much rotation, so the pseudo-Newtonian potential, this also very nicely written into around to the 3 Shivashi radius region. So within this one, we need more actual black hole solution to there. Okay, so this is a so the Shivashi metric is in the Boyer-Gates coordinate. R equal to gm over c square is a coordinate singularity. So this is the surface of the infinite radiation redshift. It means the we say this event horizon position over there. So exterior the Shivashi solution can be extended inside the horizon with some specific spatial coordinate as to the vacuum solution. So this is the metric it will behave at the Shivashi radius. So this is some the coordinate. We say this is the Eddington frequency coordinate or laminar coordinate, or the curve black hole case we usually using for the Churchill coordinate system. This is also ingoing coordinate passing through to the event horizon, doesn't have any singularity. So this event horizon is we say this coordinate singularity. Choosing for the Boyer-Linkes coordinate, we can see about for this singularity. But any choosing for the different coordinate, we can avoid for this event horizon to passing through inside smoothly.
Inside the horizon?
Yeah, inside horizon. So this is here. R equals 0, the true curvature singularity. So it means this is Shivashi, it's all singularity, it's happen at the R equals 0 point.
What do you mean by special coordinates?
So special coordinate means that we are follow up to the ingoing observer. Like this Churchill coordinate or the famous, I think it's Shivashi case, it's Eddington-Finkelson coordinate system. This is also ingoing for to the observer, we can think about that. In this case, we can avoid for the singularity at the event horizon point.
This only for numerical purposes, let's say in order to...
No, it's not numerical purpose. So that we also try to, sometimes we can think about what what's the effect from to the connection with the inner black hole and to the outside black hole. No, inner event horizon and outside event horizon. We can think about some special coordinate system. Try to do. Of course, numerically, this is a very, very efficient, but sometimes or some analytical calculation also consider this kind of coordinate. Yeah. Because we are avoiding for the singularity.
Yeah,
It's a coordinate. Yeah.
But then, this I understand, that
Yeah.
is, more like a boundary
Yeah.
condition
Mm-hmm.
in order to study what happens above it physically,
Yeah.
because it lacks physical meaning.
Yeah, of course.
If we trust too much in this
Yeah.
region inside.
So especially if you think about for the GRMHD or MHD wave is the how to say the max accretion onto the black hole or something for the Bromford-Snag process. Bromford-Snag process directly extract the energy from the boundary. So, but this is if you think about the black hole as a boundary condition, it's not good way. So we are consider for the ingoing observer to see about for how to penetrate the inside black hole, how to directly connect from to this energy of something. This is the important point to using for this ingoing observer coordinate. Okay, so important thing that this is a true curvature singularity is r equals 0 point. Then this singularity is, however, hidden behind the horizon. This is a Penrose is suggested that this is cosmic consensus hypothesis. Sensor, sorry, it's cosmic censorship is hypothesis. Yes, so yes, yes, yes. So and then so the horizon is no particular surface. So it's, you can move with your spaceship through to the horizon and tell us what happened to inside. But I don't know how to do it. But of course, the matter is not important for the black hole solution because this is completely for to the vacuum solution. Okay, this is a Schwarzschild black hole. So this is the orbit to the Schwarzschild black hole. So the equation governing to the geodesic equation, geodesics into space-time, it can be derived from to the energy integral given by the Lagrangian. This is the equation to write here. So here is this is omega is some affine parameter along to the geodesic position. Then for the time-like geodesics, so this is lambda may be identified with the proper time to the tau. Then the Lagrangian is written to here like this. So this is time. This is a derivative to here. So calculate for the respective this canonical momenta. This is the p.
Excuse me.
Yep.
How are you defining lambda as a geodesic parameter?
Lambda. This is the position.
Normal or is the proper?
I think this is the proper. To the. So it means to the is a.
It cannot be the proper time because it doesn't apply to photons, right?
It's not
Yeah.
time. It's the parameter, the geodesic parameter.
It's
Or
just
the
some
derivation
number.
is the coordinate.
I think it's the parameterization of the proper time, and then you can map it from 0 to 1, and then they use that parameterization as more efficient, I think. I don't remember.
Yes, because it's in the Lagrangian.
Yeah.
Ademir, você
For
lembra?
massive particles,
Mhm.
you may choose lambda to be the infinitesimal length
Mm-hmm.
along
Oh,
the curve,
So it's the
along the
local
curve, along the geodesic. But you cannot do that
tangent.
for photons.
Tangent.
Yep.
Then
You cannot do that for photons.
Mm-hmm. Yeah.
But in general, the real expression of the lambda is not important.
Mhm.
Because at the end you relate the lambda with the time
Yes. Yeah.
to go from one point to the other point.
Mm-hmm.
yes, but this is tangent because
And
I think
this
the
Yeah.
doesn't matter because even for light there
Yeah.
is a finite time to go from one point to the other point.
Mm-hmm.
And this explains why it may identify the time,
right.
the time power.
Okay. So that this is.
It's
Yep.
written over there.
Yeah.
Lambda is
Yeah. So the.
proportional to
yeah.
the proper time.
So next is think about for the momenta to here. So momenta is calculated for the Lagrangian divide to the this is the partial derivative x dot alpha. So here to the pt is the t dot or theta is the theta dot is calculated. So we know to this Lagrangian already, and then to the t dot theta dot is included here. We can calculate like this is a canonical momenta here. Then is think about for the integration of the motion. So the further integrated motion is follow from the equation. It's getting for the d tau is the dpt is equal to the divide to the time derivative of the Lagrangian. This is also to the phi component is also getting equal to 0. This kind to the two integral is found to the two our constant information. So this is the pt equal to written to here as we say equal to E. It's also constant. This is a energy integral. So we say this energy is conserved. Then a second one is a phi component. This is we say this is also L. This is also the angular momentum is related here. So based on this geodesic, we have a two integrate at the point. So this is one is the energy, one is the angular momentum. Yeah.
Please
No,
go
okay.
back.
Yep.
Yes, this one. Because you are using geometry, the geometry r, theta, and phi.
Ah, yes, R theta
So
phi, yes.
you are using
Spherical coordinate, yes.
coordinates. Okay.
Yep. Yeah, okay, yes. This is a yes. Initially I said yes. This is a we using for the spherical coordinate to calculate for the orbit in motion around the supermassive black hole. So I think this is the most simplest coordinate to choosing for this one.
But then we have t.
Yep.
Small t, and we have
Yeah, tau,
tau,
yes, of course.
the proper time.
Yep, proper time. Tau and the t is also coming to here. Yep.
Right.
Okay. So based on this is here, we only first consider about for the equatorial plane. Then this is a theta contraction, sine theta function is just going to divide one, changing for this one. Then rewriting for the Lagrangian using for this E and F to including for this Lagrangian.
L, excuse me, L,
It's here.
not Lagrangian. L.
Yes, L is the angular momentum. This is one of the constant.
Okay, so could you please go back to the former slide
Yeah.
because we had
Yeah, this is the
Lagrangian.
Lagrangian. This is the curl L.
Yeah.
Yes, a little bit confusing. Curl L is the Lagrangian. The normal L is capital L is the angular momentum.
Angular momentum. Right.
Yeah.
Just to see, okay, C you
Yeah.
defined as 1, so it's hidden.
Yep. C is, yeah, unfortunately, yeah, C is just we can drop off to the whole equation to the.
Yes, this is a mess. I hate this. I always hate this C equal 1 because
Yeah.
we lack physics when C is equal to 1. You have to go through the equations very carefully. But you know,
Yep.
I mean, this is standard. I'm not criticizing you.
No, no,
I'm
yeah,
saying
okay,
that
yeah.
it's busy even in textbooks.
Mhm.
The same. So okay.
Yep.
Okay, so when is mass? Okay. Right.
So important point is that we have two integral, so the energy and the angular momentum, and then this is getting for the effective potential. So this is effective potential. It's rewriting for the Lagrangian to here, and then this is going to the 2 Lagrangian. Then we are concerned about for the 1 or 0. This is so talk about for the massive particle or massless particle. So this is photon or some mass particle. Then find the two integrals of motion to calculate for the this is E square function and this is L part of it. Then first equation is allowed to us to define the effective potential. So now effective potential is written to like this way over there. Okay.
The effective potential
Yes.
comes from the difference.
Yes,
the-
this is
the
yes.
net-
From this is going to back, and then this is actually getting for the effective potential part.
Okay.
So energy minus to the this effective potential part to get into the this is R motion.
Right.
So this is effective potential. We can just drop it right into here. So this is Shibashi effective potential. So we are this is different of the different L value. So we are see about for the different portion to here. Also, I try to say something about for the what's the possible orbit onto this based on the effective potential. So first one point is this is most bottom point. If you think about for the this is your value, this is making for the perfect circular orbit. This radius is constant over there. Then if you think about for the number 2 point, this is between to this dipping the effective potential. This is we say this is the bound orbit also. This case is you see about for the here. So this is elliptical, but this is slightly shifted around over there. So this is but still this is bounded inside to this is the position over there. And the next is the number 3 part. The number 3 part is from if you have this energy, so you can hitting for this one inside to there. So this is we can say about for the capture of to the a particle orbit. We say this is an unbounded particle orbit. Of course, first you can start in here and then try to circulate, but finally this is fallen down to the black hole. And number 4 is that if you have enough energy of the particle, so this is particle doesn't circulate, this is directly put onto the black hole. This is we say unbound orbit, this is a bound orbit. So based on this is a effective potential, we can say about for this kind of the 4 different orbit is possibilities shown there. Okay, so now we can calculate. We know about for the effective potential getting for the what's the circular orbit, when it's happened for the unbound orbit to come. This is picturable we can see, but mathematically I would like to get in for some number there. So first is the derivative of the potential is given us to the circular orbit. So making for this derivative r with this is effective potential. The equation written to like this, and then this is made to here. So find the minimum of the max of the radius. We say this is unstable point and a stable point. Then this is a critical value. It's written to here. So now we have the square root inside here. So you know the condition of the existence of a circular orbit is L square is larger than to the 12L square.
With the c square.
Yes, I think it's c squared here.
C4, I don't know.
Yes.
I don't know.
This is a c force because mc squared. Yes, yeah. This is squared.
C4, yeah.
For the minimum is L over m. This is larger than to the square root of the 12. This is smallest possible radius of a stable circular orbit. We say this is ISCO into the Schwarzschild metric case. So this is getting for the 6m to the infinity. We get in for some stable position for the particles. But this is unstable circular orbit is coming from this is 3m to the 6m region. This is the unstable circular orbit. So we can slide the circular, but this is also after the capture to there. Okay, so this is a circular orbit for the Schwarzschild for the property. So sometimes if you know that yes, Schwarzschild black hole is position in the 6m. How to calculate this one? So we coming from this particle motion based on this equator plane, effective potential calculate, and then this is getting for the minimum one. Okay. So it's jump into the curve black hole next. So here usually a little bit rewriting for this Boyer coordinated curve black hole metric. This have more meaningful of each component. So this is a bit sometimes not familiar of this equation, but I hope you can get something information. So this is a GTT term, and then the G55 is also getting for the GT5 term, and then GRR and the G square. Yes, theta term. So curve black hole is a metric property. It's different to the Schwarzschild because they have a off diagonal term. T5 term is come up to the metric because this is here T and phi is coupling with this. So this is a related for the rotation of the black hole. Why it's coming to here? It's space-time is rotate. This is effect into here. So here I can write in for some different a little bit the quantities. Alpha is like this here. We say this is a Raps function. We are explaining also the tomorrow this one, what the meaning of the Raps function. Delta is r square minus 2mr plus a square. This is the horizon function. Rho square is r square plus a square cosine theta. This is a generalized radius. And then sigma square is right in here. This is we say this is a sigma potential. Omega is this is a flame dragging efficiency to there. And then the omega tilde is this is some cylindrical radius.
And you are defining already A.
Ah, yes. A go to the is a spin parameter. We doesn't here. So this is the angular black hole angular momentum is related for the m times A. A is a normalized up to the m. So asymptotic flatness we try to say. Of course, the Schwarzschild is asymptotic flat. Also, curve black hole is also one of the solution of the black hole, and then this is also satisfied asymptotic flat. Yep. this is gained for the alpha equal to the square. This is 1 minus 2mr. This is returned back to the Shibarshi type. And then omega equal also r equals square 3. This is, if you are far away, this is drop off to this component. And then event horizon, it's calculated for the delta equal to 0. So this is a horizon function. Then the horizon is m plus root m square minus a square. So a square is every time smaller than to m square. So this is a curve black hole definition. If this is a square is larger than to the m square, this is getting for the naked singularity. But this is out of our focus today, so I just doesn't say anything about that. But this is a yes black hole solution. So it's an important point. Event horizon position it's depend on to the a spin parameter. So this is the fastest spin case. It's become to the event horizon becomes smaller. And then a equals 0 case, it's recovered to the Shibarshi radius to the event horizon position. Okay, so this is a comparison with the Shibarshi and the curve black hole. So the event horizon is the surface at the infinity and redshift position. So here, Shibarshi is a equals 0, completely spherical. This is a spherical symmetric structure, and then event horizon to here. And then we have the singularity, it's just a 1 point, r equals 0. This is the curve black hole. Now we show about for the most extremely rotating curve black hole case. Now we are see about for some elongation of the structure of the curve black hole. So this is we say the ergosphere. This is I a little bit talk about later. This is one of the special region for the curve black hole. Ergosphere inside ergosphere, it doesn't co-rotate around the field space-time rotation. And we have two the event horizon. This is the outer event horizon or inner event horizon. This is calculation to here. So this is oh yes, it should be plus or minus here. And interesting point is that we have a singularity. It's Shibarshi to become the point, but curve black hole making for the ring singularity. This is also another different topic, the picture between the Shibarshi and curve black holes. So curve is different from the Shibarshi to curve. It's curve black hole to rotate. Shibarshi is non-rotating. But black hole property is quite different. We see many different information is come to this black hole. So uniqueness of the curve solution. This is stationary. Yes, this is coming from the black hole has a no-hair theorem something. The stationary axisymmetric solution of the Einstein vacuum equation, which is satisfactory. It's asymptotically flat. This is local Minkowskian. It's going to the far away to there. And then contains a smooth convection horizon and also non-singularity outside the horizon. Of course, if you say about the singularity outside, this is completely different. So everything outside the black hole horizon, we doesn't have anything. Singularity is everything inside the event horizon. Yeah. Back. Okay. Okay.
Yes. So this outer horizon and inner horizon.
Yeah.
What is the difference between the physical difference between the outer and the inner horizon?
This is
constrained by the ring rather than by the singularity.
No, the
because inside the ring there is a singularity as well.
Yeah, this is a singularity, actual singularity. The outer horizon, inner horizon is both coordinate singularity. This is same out to the Shibarshi way. Because we are considered for the Boyer linkage coordinate, and then this is getting for the lambda is here. So this is GRR term is going to equal to 0. I think this is the same. This is yes definition going to infinity. This is the definition of the horizon function of there. So this horizon function is calculated for this the black hole size, and then this is the r squared it's come to here. This is, should be plus minus to here. Then this is gained for the inner horizon and outer horizon. So sorry, I forgot to this one, the plus and the plus or minus. So this is just a coordinate singularity. So usually we can, tomorrow I little bit talk about for the Cartier coordinate. This is also one of the coordinate system to the penetrate for the horizon. But this is, no, outer horizon. Outer horizon penetrate, but
down to the
yes. But inner horizon have some, I think still inner horizon have some singularity. So we should pass into the outer horizon, but doesn't pass into the inner horizon. This is, Cartier coordinate is the properties there. Okay, so going back to here.
But
And
the shadow actually is above the outer horizon, right? For instance, the shadow
okay.
is above.
No, it's a shadow. It's coming from to the mostly coming from to the outside to the photon unstable orbit.
Right.
So this is we say this photon ring. So I say about for this unstable orbit coming from to the photon. This is the final region of the actual emission coming from to the.
Penetrates outer event horizon.
No, outside of the horizon.
Right.
So at this shadow side is every
You
time.
said unstable, down to unstable orbit.
Yes, the unstable orbit. It means to the even for this photon, it's going to enter to the black hole. It means to the we cannot catch in for the emission from to this region.
That's true, but in the Schwarzschild should be inside.
The singularity is inside. So it's okay. So the ISCO is outside. The horizon region. No, it's the unstable. The orbit. Its final unstable orbit. It's inside the ISCO. But inside of this is an unstable orbit. Everything going to the black hole. So we doesn't have anything. But still, this inside is yes. So I should be better to here. So this 3m is this is the final unstable circular orbit to get in for the emission.
Yes, because this is inside.
Yeah, this is yes, but still this is 3m. Is a horizon is a 2m. So still outside the horizon. So black hole shadow side is getting for this side of it. So not we can touch in for the event horizon. This is that sometimes misunderstanding. Okay, so we can see about for the shadow side structure there. This side is
Goes
yeah
inside the ISCO.
inside inside the ISCO, but not outside. This is minimum is the out stable
But
circular bit.
I have a very naive question
Yes.
regarding to the lapse factor.
Yes.
Is the lapse factor
Mhm.
the factor that will convert the proper time to the observed
Yep.
time?
Mhm.
Okay, because it's interesting because, for instance, in Latina++,
Yep.
You should normalize the magnetic field or another variables
Yep.
by the factor and
Yep.
by this factor.
Yes.
And I don't understand why you need to do this using the output files. Why you need to normalize
Normalize.
the variables by the lapse factor.
Yeah, because the output files
Hmm.
come.
Interesting. Okay. I'm never using for this kind of thing, but I think you compare about for to the definition of to the our. I think that we can really be touching about for the tomorrow. So what's the four magnetic field definition from to the Komisarov original one, and then to the Gamis the papers, and Ham papers, and to the Valencia formula is slightly different. I think this is between this Ham cone and the Valencia formula our using factor alpha is difference. So maybe this is something difference. So that we can calculate alpha or divided alpha or something. I think it's maybe you can see about for the what's the calculation to the original equation. This is if conserved variable. Yes. This is if you maybe you can see about for the Nobel's papers, because they are calculated for to the variable to calculate the primitive variables. So this is originally getting for the conserved variable to the Valencia formula way. We need addition of the alpha term. So because of this, the alpha term is different between to the definition of to the Valencia formula and to this Ham's definition.
What was the question?
This is why is the lapse function alpha is including for here.
Normalization of what?
Of the variables of the output files, for instance, of the HARM or Latina++.
Yeah, that maybe tomorrow. Yes. Yeah, I think this is related for the formula. What kind of formula to use into this?
Everything that is asked in here is relevant. So please, students, don't be shy. Ask whatever you have in mind is important because you have this doubt in your mind right now. So don't keep it for you, right?
But I agree that you can postpone.
This is very relevant right now. Right?
Yeah,
And then
I think
we
yes.
can repeat this tomorrow because
Yep.
all this, all the students can get some insight on this, right?
I think it's
Don't be shy to ask.
this is related for to the contour prim calculation. I think it's starting for to the contour prim, they are calculate for the alpha first its term. Then my expect as in the plus plus it's just dumping for to the this contour prim using for the alpha b I. Then before to getting for to the data, just divide to the alpha. So maybe you can more carefully see about for to the equation or before to contour prim after the contour prim. Yeah, maybe you can see get this. Then, okay, so this is a stationary black hole solution. We have a now, based on to the no hair theorem, we only have a 3 hair in the black hole. I think you know. This is the mass and angular momentum and electric charge. So combination of these 3 quantities, we can write in for to the 1, 2, 3, 4 different solution to the now it's a black hole. Here I can show about for the Shibashi black hole. Shibashi black hole only have a mass. And then I can show about for the Kerr black hole have a mass and to the angular momentum. Then also that we have a Leibniz solution black hole. This is including for the mass and to the charge. And in the Kerr-Newman solution, we have these 3 information: mass, angular momentum, and charge. But in the nature, what the charge have the black hole? This is one of the questionable point, because plasma looks like a charge neutrality, so that this kind of charge is maybe sometimes positive, sometimes negative, but in the long time, I think this is going to someone at a neutral point. But this is also we don't know yet. And sometimes one of my colleague simulation show about for the some the pulse of a magnetic simulation. This is show about for the like this Kerr-Newman type of the black hole is developed. Understand? Yeah.
When plasma approaches the horizon?
Yeah, this is the some mass accretion is on to go into the proto-neutron star type and then to suddenly go into the black hole. But this is black hole formation. It's something which including for the magnetic field effect of resistivity. They are favored to making for the some Kerr-Newman type of the black holes made up. But maybe this is I think this is short time scale to develop for this kind of human. But after that, they made to changing for the charge neutrality, then going back to the Kerr. But don't know yet. This is one of our current, interesting point. First I see it's something wrong, but it looks very interesting point there now. Okay, so this is the Freeland's no-hair theorem. Of course, if about the alternate theoretic gravity, this doesn't matter about for this mass. We are additional things about for the additional charge or some mass. Yesterday, I can talk about the dilaton black hole, also including for the dilaton, the charge. This is one of the property of the black hole. So this is one of the case.
Just a comment about charge
Yes.
in black hole.
Mm.
We believe that the universe is neutral for,
Yeah.
for charge, no?
Mm.
And perhaps this happened because the universe is closed.
Yeah.
If the universe is closed, then the net charge within the universe should be 0.
Yes. Mm-hmm.
But some people believe that a Heister-Nordstrom
Mm-hmm.
black hole, that is a black hole that has mass and charge,
Yep.
may be dynamically generated in a few times
Mm-hmm.
during the collapsing process.
Mm-hmm.
And for instance, Rufino and the
Yeah.
collaborators, they use the Heister-Nordstrom black
Mhm.
hole to explain gamma ray bursts.
Yes.
And that is a
Yes.
long ago.
Yep.
And but many people disagree about
Yes.
that.
Mhm.
Yeah, that's
But another point is that I'd like to know if you have some comment about naked singularities.
Naked singularity. Oh yes. This is yes. I'm not so much touching about for the naked singularity because this is a limitations. Yeah, curve black hole is getting for to the a equals every time smaller than to the m. But this is a equal to the yes. This is restriction to the curve black hole. But if consider for this restriction, it's not restricted. If a equals larger than to the m, what happened to here? This is getting for the just avoid the event horizon, just left over to the naked singularity. This is my as far as I remember to this one.
I beg your
But
pardon, what is the condition?
this is a equal larger than to the m.
But the
But-
point that you are when people talk about the cosmic censorship,
Yes. Yep.
this is a conjecture.
That's right. Yes.
That
That is yes.
any singularity in the
Yep.
universe may be surrounded by
Event horizon. Yes.
a null surface.
Yeah. Yeah.
That
Mhm.
should be the black hole.
Yes.
But this is not a theorem.
Yes.
And some people, for instance, in cosmology, they have discussed about which is the sign,
Mhm.
which is the sign of a naked singularity.
Mm.
For instance, in gravitational lensing,
Mhm.
they have proved that the number of images
Mhm.
is different for if you have a black hole
Mhm.
and if you have a naked singularity. And then, at least in principle,
Yeah.
We may decide if a singularity
Mhm.
is naked or if it is
Yeah.
a black hole.
Yes.
But,
You mean that it can be constrained by some observational issue? Because how is up to you to decide if it's naked or not?
Yeah.
The problem is which is the signature
Yes.
of naked
Yep.
singularities or black holes.
Yes. So
This
yes.
is until now, this is a theoretical paper.
Yep.
And then the School of Realism,
Mhm.
sociology, that they work with this a lot,
Mhm.
and they have calculated
Mhm.
some effects, most of them related with gravitational lensing,
Mhm.
that can differentiate between a naked singularity
Yep.
and a black hole. Perhaps, but I didn't read anything about the problem related to the shadow of the black hole.
Yeah. No. I think it's yeah.
Because the
yeah.
shadow should be different if you have a naked singularity.
Yes. So we are
if you have a black
the
hole.
artist is one of the our is the friends also try to calculate for the naked singularity to the black hole shadow case. Yeah, this is something is of course is a metric is so, and then we know about for the photon orbit. Unstable orbit is one of the is unstable to catch up for the naked singularity. So we can similar pictures we can see.
I believe that to simulate,
Yeah.
it is the effect.
Yep.
And compare. Suppose that
Yes.
in some way a naked singularity
Mhm.
has been dynamically generated.
Yep.
There
Mhm.
are many processes that can generate a naked
Mhm.
singularity. But from the point of view of the observation,
Yeah.
suppose that the naked singularity exists. So it should be perhaps interesting
Mhm.
to know how these observations related with the
Yep.
shadow of the black
Mhm.
hole
Yep.
can distinguish between
Mhm.
a naked
Naked
singularity
yes.
and a black
Yes.
hole.
I think yeah. Yeah. yeah.
It's only a transient effect.
This is
You
a
can
yes. So
survive.
the problem yes. One point is yes. So the how stable of the naked singularity. This is also one of the debating point. And then, as far as I know, some naked singularity have some instability. So this is not stably longer. But of course, this is physically very interesting point of view. But the observationally, we can distinguish between the black hole and the naked singularity.
One possibility is that in the collapsing process,
Mhm.
suppose that you have a high mass star, in the collapse process,
Mhm.
probably the vacuum,
Mhm.
the vacuum, the vacuum state of the matter
Mhm.
can be a time-dependent quantity.
Mhm.
For instance, if the matter is very collapsed, and the matter in another place is a star, a normal star,
Mhm.
and probably the vacuum of
Mhm.
this state are different. And if when the star is compressed to form a singularity,
Mhm.
perhaps the existence of this variation of the vacuum
Yeah.
can alter,
Mhm.
can modify the final state.
Mhm.
And
For
therefore,
instance,
you may
forming
not have a black hole.
Yeah.
You may not have a black hole.
Yes, it is.
One
Yeah.
possibility
Yes, yes.
is to one possibility is don't form a black hole, but
Yeah.
another possibility thereby avoiding the singularity.
Mhm.
But another possibility is to form a naked
Yeah.
singularity. And
So-
then perhaps it should be interesting to see the papers about naked singularities of,
Mhm.
of Ellis and collaborators,
Mhm.
and try to simulate that and to show that, okay, this is the difference
Mhm.
of the shadow provoked by a singularity
Yep.
that
The artist is
has
yes,
an
the
horizon,
yeah.
and another singularity that has no horizon.
Yeah, artist is one of the our colleague has already such kind of work as far as I know. And this is analytical work, doesn't do any simulation work, but someone has already insights about for this kind of work already about for the black hole shadow. Maybe I'm looking for some papers. I think if you are interested, I can give the papers also. Okay, so so it's going to the this is a black hole solution. Then this is what's the ergo sphere and the frame dragging effect. So this is a black hole. Now it's the curved black hole. Therefore, this is inner horizon, outer horizon, and then this is static limit. We say inside this is a static limit, and to the outside the outer horizon, we say this is ergo region of there. Ergo region is no matter how we can go into the any kind of orbit, the particle moving there, but black hole every time this is frame dragging making for the co-rotate of the black hole rotation direction. Here, this is black holes rotate on this spin. So the one of the orbit is opposite spin, but this is co-rotate anything there. Even for this one, it's opposite case, but enter to the ergo region, they are every time co-rotate. So ergo sphere is a very interesting point of every time this is co-rotate around to the black hole based on the frame dragging effect. So ergo region, so ergo means that this is energy. So all the spin energy, the black hole is lies at outside the horizon, so it can all be extracted based on the theory now. For the maximum rotation curve black hole with the mass is m, its spin energy is around to the 29% of the mc square. Two famous energy extraction mechanisms. So one is the Penrose process. This is the particle splitting inside the ergo sphere. And second one is the Brown-Forsythe process. This is the black hole spin twisted magnetic field to extract the energy through to the electromagnetic waves. As far as I know, tomorrow I can touch a little bit about. I think tomorrow is Friday. Talk about the Brown-Forsythe process a little bit. But this is a famous two process we have to this extract energy. So again, talk about for the geodesic in the equator plane, about for the curved black hole. So curved black hole have, of course, the additional matrix. So we have a Lagrangian is a little bit complicated. So now it's a t dot term, t dot phi term, r dot, and the phi dot term. Theta dot is just drop off because we consider about for the equator plane only. Then the conservation law is similar. We have a pt term is getting for the energy conservation, and then p phi term getting for the angular momentum conservation. Then this is written to this kind of way. I try to avoid this the deviation to here, but we have a correction up to the a term between to this one. So maybe if you compare about for to the Shibashit version to there, then the radial equation is rather complicated to written to here like this. Then again, this is the radial equation. So looking for the double roots part. we are getting for the energy and the angular momentum is written to this kind of way. Then looking for this is the triple root part, we can get in for the ISCO radius part. Then ISCO radius is written to this kind of equation, and then this also including for the Z1 and the Z2 the component. This is Z1 is written here, Z2 is component here. So everything is getting for the some the correction up to this the spin parameter A term, and then this is a bit complicated, but this is ISCO position. Why we can put on the minus or the plus? Because this is ISCO position, it's co-rotate and counter-rotate of the black hole spin. Then this position is different to the plus and minus direction. So this is also an important property of the black holes rotate one direction, but particles also have a moving for the one direction co-rotate or counter-rotate. This is also another choice of case. So this is the characteristic radius of the curved black hole. So we are saying this is the ISCO position to here. Then this is the Schwarzschild position, and this is the bound orbit position, and this is the photon orbit case. Photon orbit is minimum is 3, and then the inner bound position is here, and then this is the ISCO position. I think this is 9 to 3. I think this is the bound orbit is ISCO position. Okay, so this is a curved black hole case. I can a little bit talk about there. Then this is today's summary. So space-time is a set of the all events, and it has a structure of the shared Riemann manifold with a metric tensor field G. Einstein's gravity is assumed to the connection to be the metric, and then free-falling object follow to the geodesics onto this manifold. The Einstein tensor is coupling to the energy momentum tensor of the matter in the space-time, including for the field and the vacuum. And then black hole is predicted from this is a general relativity. This is also the solution of the Einstein field equation. Then from the black hole as a no-hair theorem, the black hole has only 3 information. That is the mass, angular momentum, and the charge. So this is our today's summary. So if you have any question for today's lecture, so please raise your hand.